Welcome to the Unit 8, Section 3 video on piecewise functions. So throughout this course we have talked about different function types, and you can actually piece together a function using different function types on different intervals along the graph. Remember, when we talk about intervals, we're talking about x values. So let's start with a simple example. Recall the absolute value parent function. This parent function is an example of a piecewise function. Its graph is made up of two equations or pieces which correspond to different parts of the domain. Okay, so this graph, as you have it here, and we talked a little bit about this when we first did absolute value parent functions, it's actually two different lines. Okay, so we can actually write this as two pieces. If x is greater than or equal to 0, we can write it as y equals x. Now if you are less than 0, we can write it as y equals negative x. Now there are two methods for graphing a piecewise function. You can either graph the entire function and erase the piece you don't need, or you can evaluate the function using the specified domain and come up with points and then sketch your line or curve through those points. Choose whichever method works best for you, and then there are some cases where one method will actually work better than the other, and we'll come across those as we go along. But I am a big fan of graphing the entire function and erasing the piece you don't need, because then you can at least hit your y-intercept where you need to. So let's start off with a couple of basic examples. Let's start with g of x equals 6 when x is less than or equal to 1, negative 1, or x minus 2 when x is greater than negative 1. So we're just going to graph both of these. And we're going to start with 6. Okay, so we know when it's less than or equal to negative 1, so we're going to start with negative 1, that it's just this constant function that goes this way. Then we know that it's x minus 2 when it's greater than negative 1. And we know that the intercept is negative 2, that's our y-intercept. And we know that it's just, the slope is 1, so we can graph it through just like that. And then of course we have to add one thing to the end of this part because the negative 1 is included with the constant function. So you put a dot there and an open dot on the end of this one. And that gives you your piecewise function. All right, let's move on to b. So for b, we have g of x equals negative 2x plus 1 when x is less than or equal to 3, and 2 when it's greater than 3. So let's start off with the less than or equal to 3 part. We know that the y-intercept is 1, and we know that our slope is negative 2, which means we're going to go down 2 over 1, down 2 over 1, and we're going to continue to follow that until we get to 3. And then we'll draw our line from there, making sure we go through our y-intercept, which is 1. And so you end up with a line like this. Then we know it's just the constant 2 from 3 on. So we'll graph our line here. And we know that we are not including 2 at this part of the function because it's included in this part of the function. All right, we're going to continue on with a few more examples. So again, we have a line and a constant. The line starts at 4 and goes to greater than 4, but it does not include 4. So this is a case where we're going to have to graph the entire line first. So we know that our slope is 1/2 and our y-intercept's negative 3. So our y-intercept's here, our slope is 1/2. So we can go up 1 over 2, up 1 over 2, up 1 over 2. So we know that we are here, right, at this point. We've hit the 4. So you don't exactly have to sketch it, you just have to follow from the y-intercept where you're heading. So we know our line is going to go from here and continue this way with that slope, up 2 over 1, up 1 over 2, up 1 over 2. And we know that we are not including the end, so we put an open dot there. Now let's focus on the rest. From -3 to 2, we have a constant, and that is at -5. So from -3 to 2, and we will not need an arrow for this part. So we go from -3 to 2, and for some reason I can't get a straight line to draw, so that's okay. I'll just do it manually. It won't look quite as straight, but it will still get the job done. Now we are including the 2 on this end, so we put our dot here, and then we put our open dot on the other end where we're not including it. All right, for D, let's take a look at what we have here. So we have -4 when x is less than or equal to 0, and then we have this line, 3x minus 4, between 1 and 3. So we're going to start at our y-intercept, -4, and we're going to go to 3, from 1 to 3. So we start here at -4. Our slope is 3 over 1, so we go up 3 over 1, and we are where we start at 1. So now we're going to start our plot, and we're going to go up and over. And again, we don't need an arrow on this one, so I will do this manually. So we're going to go up 3 over 1, up 3 over 1, and we stop at 3, and we're not including the 3, so there will be an open dot here. And we're just going to put our closed dot on this end, and then we graph through as straight of a line as we can. Then we have, on the other end, -4 when we're less than 0. So it's just a constant line that goes in that direction. And we do include the point. So here we have a skip, but it's still a function, right? We can still do the vertical line test on either of these, and we have a function because it doesn't fail the vertical line test. It's not continuous, but it is still a function. All right, let's go to the next 2 examples. We have these 2 pieces. So let's start off with the x squared part, okay? So this is when x is greater than or equal to 0. So we're going to have a point at 0, 0, and then we're just going to follow the sketch of a parabola just on this side of it. It's not stretched, it's not compressed, and it's not translated, so that makes it fairly simple. So we go over 1, up 1, because 1 squared is 1. We go over 2 and up 4, because 2 squared is 4. This is all graphing that we know how to do. And then the next one would go to 9. So you would end up with this part looking like this. Let's put a little bit more curve into that. And then the other part, we have x plus 1. So that's going to be a linear function. And the y-intercept is at 1, but we're starting at -3. So we go over 1, down 1. Or I should say, yeah, over 1, down 1, over 1, down 1, over 1, down 1, till we get to 3. and we know it's increasing coming from negative infinity. And we just put our point on the end here to show that we include the negative 3 on that end. And I'll make the point on this end a little bit more prominent as well. All right, for f, we have a quadratic again. This time it is translated to the right, or I should say to the, it is translated down by 2, okay? If it was right or left, it would be in here with the x. So it's translated down 2. So we know that that's where our vertex is going to be. We want all values of this parabola greater than negative 1, but not including. So we will go over 1, up 1, because it's not stretched or compressed. And we will plot our open dot here. We go over 1, up 1 on this end. We go over 2, up 4 here. We go over 3, up 9. So that would put us here. And then we can draw our parabola from there on that part of the domain. And now let's go to the linear part, or actually it's not even linear, it's a constant part. As we go less than or equal to negative 1, we're going to be at negative 4, which puts us here. And a line that just goes this way, and we include negative 1 on that end. So we just put a dot there. All right, continuing on with examples, let's go to G. This time we've got 3 parts to the graph that we are going to sketch. So let's take these one by one. Let's start with the top one, x plus 3 squared. So now we know that it has been translated to the left 3 units. So our vertex is going to be here. Now we want all values to be quadratic less than negative 2. So we know we're going to have a hole here as we go over 1 and up 1. And then we can sketch the left-hand side as normal. And then we'll draw our line through. Now let's take a look at the next part. We've got a linear equation, and this one is got a x, or I should say a y-intercept of negative 1. So we know, since we're between negative 2 and 4, 0 is going to lie along that, so we can go ahead and plot a little point there if we want. Now our slope is going to be 1, so that means we're just going to have a line that has a slope of 1 going from negative 2 to 4 and going through that intercept. And we also know that we're not going to include the point at 4. So it's going to go from here down to here at x equals negative 2. So I'll put my close point there for that end. And then we'll sketch the line. Now for the last piece. Another linear equation, this time with a y-intercept of 2, and this time the slope's going to be negative. So what I'm going to do is, since this is a simple enough slope, we're just going to follow this down. So we've got down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1, until we get to 4. And so we're going to plot our point there. And then we will plot our line from there. And so that is our final graph that's got all 3 parts to that piecewise function. Again, it is a function because at no point going from left to right do we have 2 values of y for a value of x. So it passes the vertical line test. All right, let's take a look at h. H also has 3 parts to it. Let's start with the first part. The first part is going to have, and this should be x squared. So let's add a square to that. Might as well to make it more interesting. X squared plus 4. and then we have negative 3, and then we have x minus 5 squared. So this one, we're actually going to have, let's make one other adjustment to this. Let's make this x plus 4 quantity squared. That way we have it moving to the left 4. So when we do that, we're going to go to left 4, and this is where our vertex is going to be. And we're including the vertex. And then we're just going to do the left-hand side of this parabola. So over 1, up 1, over 2, up 4, over 3, up 9, which takes us off the graph. So from here, we're going to do our sketch. So there's the sketch of our first part. Now let's go on to the next part. We've got a constant between negative 4 and 4. We're not including the ends, and it's going to be at negative 3. So here we're going to have an open dot, and then we're also going to have an open dot on the other end of it. And in between, we're just going to have a horizontal line. And then finally, for this last part, we have another parabola, but this time it is translated to the right 5. So we're going to have our vertex here. We're going to go over 1 and up 1 here, and we will include this end. And then we're going to go over 1, up 1 here, over 2, up 4, and so we draw our parabola from there. And there is that piecewise function. Okay, let's move on to the last two examples of graphing just to make sure we have this down. We have one more where we have 3 pieces, so let's graph those 3 pieces. Where x is less than negative 3. Again, I have a misprint on this version. Let's make that squared like that, so that we have a translation to the left by 3. This is also where our vertex is, but we're not including the vertex. And then everything that's below it. So over 1, up 1, over 2, up 4. And then we can draw a parabola from there. Then for the next part, we are going to do the other parabola, or another parabola. This time it's going to be concave down because we got the negative in front of the x squared. We could think of this as x squared, negative x squared plus 4. So that means we are translated down by 4. So our vertex is going to go here. And we have a concave down, or actually I should say we're translated up. That would be the correct way of looking at this because we're plus 4, right? This is where you have to be careful, plus 4. So we're going up. And then we're going to graph our parabola based on this negative x squared. So that means we're going to be concave down, which means we're going to go here and here for our next points. And we're going from negative 3 to positive 2. So we'll continue to graph until we get to negative 3. So over 3, down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And this one is going to include the end. And then when we get to 2, that will also include the end, which would be here. And so from here, we are going to graph the line in between the 2 end dots. So there's the parabola for the second piece. And then the last part is much simpler. It's just a constant. And we know that we are not including the end here. So we're going to do an open dot. And then we are just going to graph the line out from there. So there we are. For this last example, this is a little bit different than the ones we've done before. So we've got 2x plus 3 when x equals 2, and then x minus 3 when x is not 2. So what this means is it's going to be x minus 3 everywhere, but for that one point. So let's go ahead and plot that line that goes everywhere else. Okay, so we have x minus 3, so we have a y-intercept of negative 3. Our slope is 1, so we're going to go up 1 over 1, up 1 over 1. So here, I am at the point where we are going to be skipping. Everywhere else, we're just up 1 over 1, up 1 over 1, all the way in each direction. So we can go ahead and sketch the rest of this line. And then last but not least, we're going to find where this line falls at x equals 2. So we have an x-intercept of 3, or y-intercept of 3, and then we have a slope of 2. So up 2 over 1, up 2 over 1. And so that point for 2 specifically is going to go here. And what we call this is removable discontinuity. It's a function. It passes the vertical line test. It's just discontinuous, like the others have been. This is called removable discontinuity. Okay, so we've done plenty of graphing of these things. Now let's move on to evaluating piecewise functions, which is considerably easier than coming up with the graph. And it's a lot more practical as well. So to do this, we are going to evaluate the piecewise functions by plugging in the value that is requested for that domain that is requested. Also, this is a good opportunity here to describe what a step function is. A piecewise function that is constant for each interval of its domain is called a step function because the graph looks like steps. You've got horizontal lines all over the place, so it's like taking steps up and down. And that's what A is here. So let's evaluate what f of negative 2 is. Well, we find where negative 2 is in the domain. It would be in this section. So x is less than or equal to 0. And we find that our value for f is negative 5. For f of 1, we are in between 0 and 3, so our value is 4. And then for f of 5, we're greater than 3, so our value here is 12. Now that's about the easiest that it can get for evaluating. It does become a little bit more work when you have to actually do a little bit of math, but it's not too bad. It's fairly straightforward. So f of negative 3, we're going to use this part of the function, this first line, because x is less than 0. Negative 3 is less than 0. So we're going to just plug in to that part. So 6 times negative 3 going in place of x. And when you do that math, you end up with negative 19. For f of 0, well, since we're doing f is equal to 0, or x is equal to 0, then we need to use the portion where we have the equals part. So that's going to be 7 times 0 plus 3, which gives us 3. And then obviously 4 is greater than 0, so we're going to use that same part for 4 as well. And when you do that math, you end up with 31. 28 plus 3. All right, for C, when f is negative 3, we have to use this portion of the function where x is less than negative 1. So we're going to plug in negative 3 into that part. So on the top, you get negative 3 squared, which is 9. 9 minus 9 is 0. 0 divided by anything is 0, so you have 0. For f of 1, or I should say f of 1, yes. For f of 1, x is greater than negative 1, so you just have 6. And then for f of negative 1, we have to use the equals to portion. So we're going back to the top part. negative 1 squared minus 9 over negative 1 plus 2. The top part, we get negative 1 squared, which is 1. 1 minus 9 is negative 8. Negative 1 plus 2 is 1, so you end up with negative 8. And then finally for D, f of x equals 3 different things depending on where you are in the domain. So for 2, we find the part where we have 2 defined. Well, it's not this top part, and it's not this part, but it's not this third part either because there's no equals to. So since there is no part of this function that I can plug 2 in, then f of 2 is undefined because there is no value of 2 that works in this function. It's not defined. Now f of 3 is defined. That's for this third part, so we're going to do 1/3 times 3, which gives us 1. And then for negative 8, we're in this portion of the function, so we have 2 plus negative 8, which gives us negative 6. So you'll see there's not really that much to evaluating it. You find the portion that you need to put it into, and then you plug it in and find out what your value is. Now let's talk about writing piecewise functions. So if we're given a graph, we can write a piecewise function based on the graph that we're given. So let's talk about this. You may have to extend the parts of the graph to get the information you need, such as the y-intercept. And we will do that as we come to it. The nice thing about this first example, we know what both of our y-intercepts are. And we know that our slope is 1 for this part and 1 for this part. So we can simply write down what our piecewise equation is pretty simply. So we know that it's x plus 2, because that's our y-intercept for the first part, and that is when x is less than 0. And it's less than because it's open here. Then it's simply x, because the intercept is 0, when x is greater than or equal to 0. And it's equal to because we've got the solid dot here. For this next one, we've got 2 straight lines again, so we're going to use slope-intercept form once again. So for the first one, our intercept appears to be 1/2, or 1.5, which would be 3/2. Our slope is 1 over 2, which is 1/2. So for the first part, we can say it's 1/2 x plus 3/2, which is our intercept. And that is for when x is less than 1. Then, when x is greater than or equal to 1, and we could put the equal to on either part of this if we wanted to. It doesn't really matter since it's the same value at 1 either way. But we know the slope is negative. It's negative 1, so that's negative x. And our intercept, if we continued the line through, would be at 3. So negative x plus 3 when x is greater than or equal to 1. For C, we have 2 straight lines again. So we're going to have f of x is equal to, and this is going to be a 2-part piecewise function. The first part, the slope is 1. The intercept is 0, so we'd have x when x is greater than 0 or less than 0. Got to make sure you write that correctly. And then the slope here is 2 over 1. So we'd have 2x when x is greater than or equal to 0. For D, we have 3 parts. So we're going to have a 3-part piecewise function. For the first part, if we were to extend this, the slope is 1. If we were to keep going, our y-intercept would be 2. So we have x plus 2 for the first part. We'll take care of our domains here in a moment. Let's go ahead and write our equations down. Here we know that the intercept is 3 and the slope is still 1, so we have x plus 3. And then for this last part, if we were to extend this back, because the slope again is still 1, if we extend this back, our intercept would be 1. So now let's take care of the sections of the domain. So for this first part, we are when x is less than or equal to -1. And then when x is between -1 and 1. And then finally, when x is greater than or equal to 1. So there's different strategies that you can employ. You can write all the equations, then take care of your domains. It all depends on what you're comfortable with. All right, for E, we have 2 pieces, and again, they're both linear, so that makes it fairly simple. So this first piece, we have a slope of 3 over 2. So we're going to follow this slope, and if we keep going, 3 over 2, our y-intercept would end up being between 4 and 5, so about halfway between, which would put us at 9/2. So our y-intercept for the first part is 9/2, our slope is 3/2. So we have 3/2 x plus 9/2. The second part is a constant, it's just -1. Our first interval is going to go from -infinity to -1, so it's when x is less than -1 because we do not include it. That x gets included here when x is greater than or equal to -1. For F, we have 2 straight lines, 2 linear functions, and a constant in between. So this one we'll have to project out a little bit. We know our slope is 3, so we'll go ahead and write that part. Our slope is 3. Now we've got to figure out what our intercept is. Well, if we keep this going, up 3 over 1, that's at 7. Up 3, 7, 8, 9, 10, if we project it over 1, we hit the axis. So our intercept would be at 10. It goes off the graph, but that's okay. We can still kind of figure it out from there. Then we have a constant. We're just at 4 for the second part. Then here, we're the same distance from this side. In fact, this is the same line. It's just negative slope this time. And if you were to work it backwards, you still have the same y-intercept of 10. All right, so from here, we have x is less than or equal to -2. For 4, we're just going to say that's when we're between -2 and 2. And then for the last part, when x is greater than or equal to 2. All right, so now let's do a couple more examples. These are the last 2 examples for this part. And these examples involve some quadratics. And quadratics are actually easier to handle writing the equations than you would think. So this part has 3, so we're going to have a function with 3 parts to it. And those 3 parts are a quadratic, a quadratic, and a quadratic. So let's start with the first one. We know where the vertex is for each of these. The vertex here is at -3. So we translate it, and let's look at the shape. It's not stretched, it's not compressed. This one is not stretched or compressed. This one's not stretched or compressed. So we don't have to worry about stretching or compressing on any of these, okay? So now we know that this was translated to the left 3. So we write that by doing x plus 3 squared, quantity squared. The second piece was translated down 2. So that's going to be x squared minus 2. And it's also concave down, which means it's going to be negative x squared. And then finally, for the last part, we're translated to the right 4. So that's going to be x minus 4 quantity squared. And now we're going to put our different parts of our domain. So the first part applies when we are less than or equal to 2, negative 2. This part applies when we are between negative 2 and 2, but we do include the 2 part. And then this last part is when x is greater than 2. And now let's mix up a couple of lines. A line, a linear function, a quadratic function, and a constant function. Let's do all 3 together. So for the first part, it's linear. So let's take care of that. It's got a slope of 2. And then the intercept, if we follow this through, up 2 over 1, up 2 over 1, the intercept would be at 3. Then we've got a quadratic. It's not stretched, it's not compressed, but it is translated down 2 and over 1, over to the right 1. So we're going to have x minus 1 quantity squared to account for it going right, and then minus 2 to account for it going down. And then the last part we have is just constant, it's 5. And so for our domains, this is when x is less than or equal to negative 2. This is when x is between negative 2 and 3. But we include the 3 because of the solid dot there. And then when x is greater than 3, gives us that constant function. So it's all a matter of just taking the pieces. You know how to identify these things. You know how to write equations from these things individually. You just put it all together into a piecewise. All right, the final section of this section of notes, the final part of this section of notes, involves taking a look at piecewise function applications. We're just going to do a little bit of how this would look, and it's not as complicated as you would think. So there are many instances in the real world where piecewise functions can be useful, and let's just look at 4 of them. So for example 4, your favorite dog groomer charges according to your dog's weight. If your dog is 15 pounds and under, the groomer charges $35. If your dog is between 15 and 40 pounds, she charges $40. If your dog is 40 pounds or over, she'll charge $1.50 per pound. Write the piecewise function that represents the cost for grooming for a dog that weighs X pounds. Then use that function to estimate the cost of a dog that weighs 50 pounds. So let's write our piecewise function first. F of x equals, and we're going to have 3 parts. So the charge, if the dog is 15 pounds or under, is $35. 35 for 15 and under, so x is less than or equal to 15. Now, if the dog is between 15 and 40 pounds, then it's going to be $40. So that's when x is between, let me write this over again. That's when x is between 15 and 40. Then she charges $1.50 per pound. So 1.5 times the dog's weight, which is x, when the dog is greater than or equal to 40 pounds. So that's our function. So we're asked to find the cost for a dog that weighs 50 pounds. So we want to find f of 50. Well, that would fall in this last one, so it would be 1.5 times our x, which is 50, and so that would give you 75. So it would cost $75. to groom a dog that weighs 50 pounds. And as always, a word problem requires a word answer. It will cost $75 to groom a dog that weighs 50 pounds. Let's go to example 5 now. A car rental company charges a flat fee of $45 to rent a car. In addition to that, you must pay a fee per day you rent it. If you keep the car for 3 days or less, it'll cost $7 a day. If you keep the car longer than 3 days, it'll only cost $5 a day. Write a piecewise function that represents the cost of renting a car for X days. Then use the function to estimate the cost of renting a car for 7 days. So we have a two-piece function for this one. So it's going to cost $45 either way up front. So we're going to have 45 plus some amount. If we keep the car for 3 days or less, it'll cost $7 per day. So $7 times the number of days. If we keep it longer than 3 days, it'll only cost $5 per day. So 5 times the number of days. Now let's make sure we get our domain right. If we keep it for 3 days or less, so x is less than or equal to 3. Then if x is greater than 3, we do the second part. And we want to know how much it would cost to rent the car for 7 days. So f of 7 equals, we're going to use the bottom part here, 45 plus 5 times 7. And that works out to 80. And again, we need a word answer to sum it up. It will cost $80 to rent the car for 7 days. All right, example 6. You are looking to rent a boat this summer. The local marina charges a deposit of $100 to rent. In addition to the deposit, you pay $35 an hour if you rent for 4 hours or less. You will pay $45 an hour if you rent it for over 4 hours. Write a piecewise function that represents the cost of renting a boat at the local marina. All right, let's first of all write our piecewise function. So we're going to have two pieces again. You have to pay a deposit of $100 either way. So we're going to have $100 plus some amount. It'll be $35 an hour if we rent it for 4 hours or less. So that's x is less than or equal to 4. It will be $45 an hour if it goes over 4 hours. So 45x, that's when x is greater than 4. So now we want to see what the cost is for renting it for 3 hours. We're going to use the top equation. F of 3 equals 100 plus 35 times 3, and that works out to 205. So it will cost $205 to rent the boat for 3 hours. All right, and the final example. A store charges $15 per shirt for orders of 50 or fewer t-shirts, $13.50 per shirt for orders of 75 or fewer but more than 50 t-shirts, and $12.50 per shirt for orders of more than 75. We're going to write a piecewise function and then find the cost of 40 shirts. So this one will require 3 pieces. So it's going to cost $15 per shirt for 50 or fewer. So 15x when it is x is less than or equal to 50. Then it will cost $13.50, so 13.5x, when we have 75 or fewer, but more than 50. So x is somewhere between 50 and 75, and we include 75 on this one. And then if we do more than 75, it's going to be $12.50 per shirt. And this is pretty common. It's pretty common to find that your amount gets discounted as you buy in bulk. The more shirts you buy, the less each shirt's going to cost. Now we want to find the cost of 40 shirts. Well, f of 40 is going to fall in the bottom one. So we'll have 15 times 40. It'll cost $15 per shirt for all 40 of those. So the cost will be $600. So it will cost $600 to purchase 40 shirts. Okay, that brings us to the end of this section, this being section 3 of Unit 8. We talked about piecewise functions. We talked about how you can graph a piecewise function, how you can evaluate piecewise functions, how you can determine what the function is by looking at a graph, and we also did some applications. So we got the last section of Unit 8 next, and that is going to be talking about systems of equations. We're going to talk about systems of equations that involve more than just linear equations, because that's something you learned in Algebra 1. We're going to take it up a step in this final section of notes.